Good day, learners. Welcome to Physical Sciences lesson. My name is Amenem Kize. This lesson is brought to you by Sci-Bono Discovery Center in collaboration with Gauteng Department of Education. Right, grade 11s, grade 12s. Today we are going to focus on knowledge area mechanics. And then under mechanics, we are only going to focus on Newton's law of universal gravitation and application of it, right? Then according to our examination guidelines, this is what actually we need to know under Newton's law of universal gravitation. One is to state Newton's law of universal gravitation in weights. And then according to our examination guideline, this is how we have to state it. Each particle in the universe attracts every other particle with a gravitational force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. Then we must be able also to solve problems using the equation F equals to gm1 m2 over r squared, where F is the gravitational force in newtons and g is the gravitational constant, and that constant is there on our data sheet or the table of constants. It is 6.67 times 10 to the power negative 11. And then M1, M2, those are the masses of the two objects measured in kilograms. And then R is the distance between the centers of those objects, which is measured in meters, right? Then also calculate the gravitational acceleration or acceleration due to gravity on Earth using G equals to gm over r squared, where G is gravitational acceleration or acceleration due to gravity in meters per second squared. G is a constant or gravitational constant. And then m is the mass of the planet. For example, if you are dealing with the Earth, so m will be the mass of the planet Earth, and then r will be the radius of the planet Earth, right? Then describe weight as the gravitational force exerted by the Earth on an object, or gravitational force exerted by Earth on objects on or near its surface, and it is measured in newtons. So weight is a force, all right? And then describe mass as the amount of matter in a body, which is measured in what? In kilograms. So you will get questions where they will say differentiate between mass and weight. So in physics, mass and weight are not the same, right? So for example, your weight, it's the force, and then mass, actually weight is the vector, and then mass is the scalar, right? So but when they say differentiate between the two, please use what we see or what you see on your examination guideline, all right? Then also calculate weight using the equation or the expression weight equals to mg, right? Calculate weight of an object on other planets with different values of gravitational acceleration. We are going to focus on that. Explain weightlessness as the sensation experienced when all contact forces are removed, all right? So this is what we are going to focus on today. It's just Newton's law of universal gravitation and its application, all right? Then this is what we are going to cover. It's Newton's laws and application, but under Newton's laws and application, we are going to focus on Newton's law of universal gravitation and its application, gravitational acceleration, mass, weight, and weightlessness, all right? Then this is the data sheet or the table of constants. So what is important here when it comes to this table is the value of G, small letter g, which is 9.8, and then also capital letter G. So there's a difference between these two. Small letter g is acceleration due to gravity. On Earth, it is 9.8 meters per second squared. And then capital letter G is gravitational constant, which is 6.67 times 10 to the power negative 11 Newton meter squared per kilogram squared. All right. And also Re, which is the radius of planet Earth, as 6.38 times 10 to the power 6 meters. And then what is also important here is this m. So this is m, or sometimes it's written as me, right? So m, it's capital letter M there, or me, that is the mass of the planet, which is 5.98 times 10 to the power 24 kilograms. So learners, today we are going to focus more on, questions under Newton's law of universal gravitation. So we are going to focus on multiple choice questions, and then remember, whether it's physics or chemistry, our question 1 is always multiple choice question. So we must learn how to answer multiple choice questions. So it would be multiple choice questions and also structured questions under Newton's law of universal gravitation, right? Then again, the important formulae when it comes to this topic, right? It is this one, and then it's weight equals to mg, where m is the mass of an object, and then g is gravitational acceleration or acceleration due to gravity, and then this is weight, which is a gravitational force that the earth exerts on object, and it is measured in in newtons. Then we also have F, all right? F equals to gm1 m2 over r squared. We are also going to use that equation. Actually, this is Newton's law of universal gravitation in symbols, all right? And then also this one or that one, which is g equals to gm over d squared or gm over r squared. And then this is the equation that we can use to calculate acceleration due to gravity. All right, then let's look at the multiple choice questions. Remember, when it comes to your physical sciences, whether it is paper 1 or paper 2 or physics or chemistry, question 1 is on multiple choice questions. So which means that we must learn how to answer multiple choice questions. It shouldn't be a surprise when it comes to an exam, right? Okay, so we have 1.1, a satellite orbits Earth at a height where the gravitational force is a quarter, which is 1/4 of the force it experiences on the surface of the Earth. If the radius of the Earth is r, the height of the satellite above the surface of the Earth is it a, which is 4r, is it b, which is 2r, is it r, or it's 1/2 what over 2r. So the equation that we use to calculate the gravitational force, it's F equals to what? G m1. So it's g m1 m2 over what? Over r squared. Okay, so if you can make r the subject of the formula here, because they're looking for the radius here or the height above the surface of the Earth, then you have r squared equals to, multiply by r on both, r squared on both sides. It will be what? G m1 m2 over what? Over f. Okay, then your r will be square root of g m1 m2 over what? Over f. Okay, then so on planet Earth we're having r equals to what? Square root of g m1 m2 over what? Over f. But now f, it's 1/4, so it's r equals to what here? So your new r, which is the height above the surface of the Earth, or the height of the satellite above the surface of the Earth, it will be r equals to square root of g m1 m2 over what? 1/4 f. Okay, so it's 1/4 f. Right, so it's r equals to square root of g m1 m2 over 1/4 what? F. Okay, which is going to be what? The square root of, this is the same as 1/1 times 4/1 what? G m1 m2 over what? Over f. Okay, so which is equals to what? Square root of 4g for what? G 4g m1 m2 over what? Over f. Okay, so this is square root of 4, it's what? Is 2, and then square root of gm1 m2 over f, right? So it's this is what, this is r actually. So this is what, twice r. Okay, okay. So our answer here will be what, will be B. All right. Then let's look at the second one. The second question: two hypothetical planets X and Y have the same mass. The diameter planet Y is twice that of planet X, right? So they're talking about the diameter here, right? So the diameter of planet Y is twice that of planet X, okay? If the acceleration due to gravity of the surface of planet X is g, then the acceleration due to gravity on planet Y will be, so on planet on planet what, X, right? So let's look at planet X. Okay, so planet X, g, it's what, g m over what, over r squared. Let me use small letter r, over what, over r squared, ne? That is planet what, planet X. Then planet Y, all right? So let's check planet Y. What is happening when it comes to planet Y, ne? So the masses are the same, right? But the diameter of planet Y, right, is twice that of planet X, right? So if the diameter of planet Y is twice that of planet X, what about the radius, right? What about the radius of planet what, of planet Y? Okay, so the diameter of planet Y is twice that of what, of planet X. Okay, so the diameter, it's from for example, if you have for those who are doing maths, you have the diameter, right? So from this point to this point, that is what, the radius. All right, then if you have from point A to point B, you are having what, the diameter. All right, then what are they saying? They are saying the diameter of planet Y is twice the diameter of what, of planet what, of planet X, right? So if, for example, this is what, the diameter name. So the diameter from point A to point B, okay? So this is planet what, this is planet what, Y, all right? So then planet X, this is the diameter of planet what, of planet X, okay? And then what about the diameter of planet what, of planet Y? It is twice that of what, of planet what, of planet X, okay? So it's twice that of planet what, of planet X. Okay, so the diameter, this is the diameter of what, of planet what, of planet X, and then the diameter of planet Y is twice that of what, of planet what, X. Ne? So which means that here you are having G equals to what? G is still G, mass are the same, or masses are the same, and then what about R now? So it is twice, okay? If the diameter of planet Y is twice that of planet X, right? Same with what, with the radius, okay? It means that the radius of planet what, of planet Y is twice the radius of what, of planet what, of planet what, of planet X, ne? So where there is R, I will substitute by what? By 2R all what? All squared. So which is going to be what? GM over 4R squared. Okay, so GM over 4R squared. Then I'm having 1 over 4 GM over what? Over R squared, which is 1 over 4. What is GM over R squared? GM over R squared is what? Is the gravitational acceleration, or acceleration due to gravity on what? On planet X, which is what? Which is G. So which means that the answer here that we're expecting is what? It's 1 over 4 what? 1 over 4 what? 1 over 4 G. Ne? Right. So So we are having what? Two hypothetical planets, X and Y, which are having the same masses, and then the diameter of planet Y is twice that of planet what? Of planet X, ne? Right. So if the acceleration due to gravity on the surface of the planet X is g, then the acceleration due to gravity on the surface of planet Y would be what? 1 over 4 g. So it's 1 over 4 what? G. So we got 1 over 4 g, which is the same as what? G over what? Over 4. So the correct answer there will be what? Will be B. All right. So as long as you understand your what? The equations that you need to use here, if they're talking about gravitational force, is F equals to g m1 m2 over r squared. Then if it's acceleration due to gravity, it's g equals to g m over what? Over r squared. And then you work with proportionality there. All right. Then let's look at the third question. The third multiple choice question. The graph below, not drawn to scale, shows the relationship between the gravitational force on a given mass and its distance from the center of the earth. All right. So the magnitude of the force on mass at a distance r from the center of earth is F, right? So the magnitude of the force on the mass at a distance r from the center of earth is what? Is F. Okay. Then which one of the following is correct, or is the correct representation of the magnitude of force X shown on the graph? Okay, so let's go back. All right, so here F, okay, so F here, the distance is what? Is R for F. And then for X, what are we looking for? We're looking for what? For F, okay, where the distance is what? It's 6r. Okay, so it's F, which is X there, where the distance is what? It's 6 what? It's 6r. Okay, so what are we supposed to do? The equation again, F equals to g m1 m2 over what? Over r squared. Okay, then that is your what? Your original what? Original F. Okay, now let's find F where now the distance, remember where the distance is r, right? So where the distance, let me write it like this, where the distance is what? Is r, F, which is the force, it's what? The force is what? Is F, which is what we have here. Okay, so which means that even where there's r squared, I can substitute by capital letter what? Capital letter R. Ne? Now let's find F where the distance is what? It's 6, or it's increased by the factor of what? Of 6. It's F equals to g m1 m2. So the masses are still the same. And then what is r now? It's 6r, but remember all squared. Okay, so I'm having what? New F, which is your X, is g m1 m2 over 6 squared is 36, and then what? R squared. Okay, then I'm having what? 1 over 36 g m1 m2 over what? R squared. Then it's 1 over 36. What is g m1 m2 over r squared? Is this original what? Original F. Okay, so the answer that we're expecting here, it's 1 over 36 what? 1 over 36 F. So if it's 1 over 36 F, then the answer will be what? There will be D. Okay, so you just use the correct equation, read the statement and check which equation are you supposed to use, and then you work with proportionality there. All right, then another question. The magnitude of the gravitational force that spheres X and Y exert on each other is F. All right, the mass of sphere X is now doubled. All right, while the mass of sphere Y and the distance between the centers of spheres remain what? Remain the same. Okay? Which one of the following combinations is correct for the magnitude of the forces that the spheres now exert on each other? All right? The magnitude of the gravitational force that spheres X and Y exerts on each other is what? It's F. Okay? So initially they exert a force of what? Of F. Okay? The mass of sphere X is now doubled, while the mass of sphere Y and the distance between the centers of the spheres remain what? Remain the same. Okay? Which one of the following combinations is the correct or is correct for the magnitude of the forces that the spheres now exert on each other? All right. One, we need to find the force or the new force after the mass of X is being what? Doubled. Okay? So, but initially, what are we having? We are just having F equals to what? G m1 m2 over what? Over r squared. Then new F, right? Or new force that the two spheres exert on each other when now the mass of X is doubled. So it will be what? Okay? It will be twice G m1 m2 over what? Over r squared. Okay? Why am I saying twice? It's mass of X that is being what? Doubled. So I'm having what? Twice what? What is this? This is what? This is F. Okay? So the new force or the new magnitude of the force that the two spheres exert on each other now will be what? Twice F. Ne? Then you are having two spheres, right? So it's your sphere X and your sphere what? Y. Right, now the force that the two exert on each other, now there will be application of Newton's third law, right? So it's twice F towards Y and then twice F towards what? Towards X. So remember, when it comes to your Newton's third law, the force that object A exerts on object B, those two forces will be what? Will be equal in magnitude but acting in opposite what? Directions. So if they were asking us about the initial force or magnitude of the force they exerted on each other before the mass of sphere X was doubled, it was going to be FF, right? Because we're told that the force that the two spheres exert on each other is F. So which means that the force that X will exert on Y will be F, and then the force that Y will exert on X will be what? Will be F. But now the mass of X was doubled. Then we had to find the new magnitude of F. And the new magnitude of F that we got, it was 2F. So if the magnitude of the force that X exerts on Y is twice F, it means that even the force that what Y exerts on what? On X will be what? Will be twice F, but acting in opposite what? Directions. So let's check which answer is correct here. The correct answer here, it cannot be it cannot be A, because now the new F, remember mass is doubled, and new F or new force that the two spheres exert on each other is what? Is twice F. Ne? So we're expecting the magnitude of the forces to be equal. Application of Newton's third law. So if you check B, the magnitudes are not equal, right? So it cannot be correct. If you check C, also the magnitudes are not equal, so it cannot be C. Then the correct answer here would be what? Will be D. So first thing that we're supposed to do here is to get the new magnitude of F, and then from there apply Newton's third law to get the correct what? The correct answer. All right. Then 1.5, a small object of mass m on the surface of planet Mars, it's m, or its mass is m, and then experiences a gravitational acceleration of g. The radius of the mass is r, and the universal gravitational constant is represented by g. Okay? Then which one of the following combinations can be used to determine the magnitude of g on mass? The magnitude of what? Of g on what? On mass. Okay? So the magnitude of g on mass, so remember the original equation from the data sheet is small letter g equals to capital letter G, which is the gravitational constant, m over what? Over r squared. Ne? So a small object mass m on the surface of planet Mars, which is m, experiences a gravitational acceleration of g, and then the radius of the mass is r, and the universal gravitational constant is represented by what? By g. Which one of the following combinations can be used to determine the magnitude of g on what? On mass. Okay, so what are we expecting here? We need the magnitude of what? Of g, the magnitude of g on what? On mass. So which one of the combinations can be used to determine the mass of to determine what? The magnitude of g on planet what? On planet mass. Okay, so the magnitude of g, if let's check A, what are we looking for? The gravitational what? Acceleration. Then when it comes to this equation, this is what is this? The gravitational constant. This is the mass of the planet. In this case is the mass of planet mass, and then this is r, which is the radius of what? Of that planet. Okay, so let's check the combination. So if you look at A, right, we have r and m. Okay, if you look at B, we are having r and small letter what? Small letter m. So we cannot use small letter m if we are looking for what gravitational acceleration, because for gravitational acceleration we need that capital letter M, which is the mass of the planet, and then the mass of the planet here, it's m there. Okay, right, so we cannot use the second one, right? And then C, gm. All right, so C, it's gm, right? We cannot remember gm won't give us gravitational what? Acceleration, because that g is what? Is just what? A constant. Okay, and then D is also g and what? So this one, it cannot be correct, and then this one also cannot be correct. We cannot use small letter what? Small letter g. Okay, so here the correct answer will be what? Will be A. The correct combination, we need what? The mass and also what? The radius, because this is always there. It's a constant. So since it is a constant, actually it doesn't have that effect on getting what? The gravitational what? Acceleration. All right, so what is going to give us gravitational acceleration or acceleration due to gravity for this planet is this combination of m and what? And r. For each and every planet, whether it's planet Mars, planet Earth, planet X, planet Y, the combination that will give us gravitational acceleration, it's the mass and also what? The radius. And g, remember, it's a constant, which is constant for all the planets. Okay, so the correct combination would be r and what? And m. Okay, then let's look at now the structured what? Questions. Okay, so this is the structured question number 1. It's we can say it's question 2, because for multiple choice questions it was question 1. Right, so the acceleration due to gravity on planet X is 2.7 meters per second squared. The radius of this planet is one third of the radius of the Earth. Okay, so then what is given here? We are given what? The gravitational acceleration, okay, on this planet. We are also given what? The mass of this planet. All right, why am I saying we are given the mass? Already from the data sheet we are given the mass of the Earth, and we are told that okay, we are not given the mass, but we are given what? The radius. Sorry about that. We are given what? The radius. All right, so the radius of this planet, it's a third or 1/3 of the radius of what? Of the Earth. All right, so we know the radius of the Earth from the data sheet or from the the table of constants. Okay, so if we know the radius of the planet, okay, then we can get the radius of what? Of if you know the radius of the Earth, then we can get the radius of what? Of this planet, which is planet what? X. Okay, then explain the difference between weight and mass. So weight, remember, it is what? The gravitational force that the Earth exerts on objects on or near its what? Surface. All right, and then remember, weight is measured in what? In newtons, and it is what? A vector. Right, and then this one is the amount of matter in a body or in an object. All right, so you are using the definitions from what? or the description from what? From the examination guidelines. So the mass, that is the amount of matter in a body, all right, which is measured in kilograms, and mass is, it's a what? It's a scalar. So that is the difference between what? Weight and what? And mass. So weight is the gravitational force that the earth exerts on an object. It is measured in what? In newtons. This is according to our examination guidelines. And then mass is the amount of matter in a body, which is measured in what? In kilograms. So that is the difference between what? Weight and mass, or mass and what? And weight. Then second question, they are looking for what? Calculate the mass of planet X, right? So we need to calculate the mass of planet X. So what is it that is given? Is the gravitational what? Acceleration, or acceleration due to gravity. And go straight to our data sheet. We copy the correct equation. The equation that we use to calculate what? The gravitational acceleration is G equals to capital letter G M over what? Over R squared. We are given acceleration due to gravity of this planet X, which is 2.7, all right? So it's 2.7 equals to 6.67 times 10 to the power negative 11. Where is this 6.67 coming from? It is also coming from the data sheet, all right? So it's a constant, so it is there on your data sheet, so there's no need for you to memorize it, all right? Then you multiply that by the mass of this planet X, okay? Then divide by what? We are given the radius. We know the radius of planet Earth, right? So according to our data sheet, the radius of planet Earth is what? It's 6.38 times 10 to the power what? To the power 6. Okay? So we can confirm the number, all right, using the data sheet. Let's confirm the number, the value actually, or the magnitude using what? The data sheet. Okay? So the value, this is what? Radius, yes, is 6 point what? 6.38, okay, times 10 to the power what? To the power 6. 6.38 times 10 to the power 6, all right. Then we are told that is 1 over 3. So it will be 1 over 3 times 6.38 times 10 to the power 6. But remember, this is all what? Squared, okay. Then we will get the mass of what? Of planet X in what? In kilograms. So what is it that we need to do here is to use our calculator to get what? The correct what? The correct answer. All right, so using the calculator, the answer that we are expecting here, it's 1.83 times 10 to the power what? 23. So it's 1.83, so 1.83 times 10 to the power 23. Okay, to get the mass of planet what? X, right? Then 2.3, determine the factor by which the weight of an object on planet X will differ from the weight of the same object on planet what? Planet Earth, all right? So remember, learners, when it comes to what? Different planets, right? What is actually different is the acceleration due to gravity, okay? So what is it that we need to know when it comes to a certain object? Ne? Object A, for example, all right? If the object A has a mass of 60 kilograms on planet Earth, even on planet Mars, the mass is still 60 kilograms, okay? But what differs is the acceleration due to gravity on those planets. But the mass of the object remains what? The same, okay? The mass of an object remains what? The same, okay? So the mass remains the same. What changes is the acceleration due to gravity. Obvious, if the acceleration due to gravity changes, it means that even the weight, right, of that object will what? Will change. Because at constant mass, right, weight and acceleration due to gravity, they are directly what? Proportional. So which means that on planet Earth, it can weigh 600 newtons, but on another planet, it will be a different story. Although your mass remains the same, but what is going to change if we move to a different planet is the gravitational acceleration. And if the gravitational acceleration changes, even the weight of an object will what? Will change. So now, determine the factor by which the weight of an object on planet X will differ from the weight of the same object on what? On planet Earth, right? So on planet Earth, we know the acceleration due to gravity is 9.8, right? Then on planet X, we're given what? 2.7, okay? So we need that factor there, okay? So what is 9.8 divided by 2.7? 9.8 divide that by what? 2.7. So it will change by the factor of what? 3.63, right? The factor 3.63. So 3.63. Okay, so that is the factor that it will change with. All right, so it's 3.63 times smaller on planet X than on planet what? Planet Earth. All right, so it's 3.63 times smaller on planet X than on what? On planet Earth. But what is important here is that even if for example my weight on planet Earth is 80 kilograms, right? So if it's 80 on planet Earth, even on planet X, planet Y, planet Mars, my mass will remain what? 80 kilograms. But what changes when I move to a different planet is the acceleration due to gravity. So if the acceleration due to gravity changes, obviously my weight will also what? Will also change. So weight of an object depends on what? On the acceleration due to gravity. All right, then let's look at another question. The gravitational force on a probe called Curiosity on the surface of Mars is 3,338 newtons. The radius of Mars is 3,390 kilometers, and the mass of the planet is 6.39 times 10 to the power 23 kilograms. Okay, then they want us to state Newton's law of universal gravitation in words, and according to our examination guideline, each particle in the universe attracts every other particle with a gravitational force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between what? Between their centers. So that is how we have to state Newton's law of universal what? Gravitation, right? Then they want us to calculate the mass of the probe. All right, so the mass of the probe, how are we going to calculate it? Fine, one, we are given gravitational force, right? So we know how to calculate the gravitational force. The gravitational force is given by G m1 m2 over what? Over r squared. Okay, then we are having two objects here, is the probe and what? And the planet mass. Okay, so the probe and the planet mass. So I can say my m1 is the probe and then my m2 is what? Is the planet mass, right? Then we are given the gravitational what? What is this gravitational force? All right, so the gravitational force, it's 3,338, ne? 3,338, 3,338, okay? Then this is 6.67 times 10 to the power negative 11. Then mass of the probe, it's what we are looking for, and then we are given the mass of what? The mass of planet is 6.39 times 10 to the power 23. 6.39 times 10 to the power what? 23. Okay, then r, remember, it is the distance between their centers. Okay, so the distance between their centers, let's check, right? The gravitational force on a probe called Curiosity on the surface of Mars is 3,338 newtons. We are fine with that. The radius of the mass or planet mass is 3,390 kilometers, right? And the mass of planet is 6.39 times 10 to the power 23 what? Kilograms. So we are given what? The radius. Okay? So the radius is 3,390. Okay? 3,390. So for us to get the mass, okay, let me just check something here. Okay. Yes. So the gravitational force on a probe called Curiosity on the surface of Mars. Ne? Oh, so the probe is on the surface of what? Of Mars. So I wanted to get that. It's on the surface of planet Mars. So if, for example, this is planet Mars, right? So the probe is here, it's on the surface. So this is going to be what? A probe. Ne? Then the distance between the centers, it will be actually the radius of what? Of that planet Mars. So the radius is 3,390. 3,390 what? Kilometers. So remember, when it comes to this equation, we need R in what? In meters, not in what? In kilometers. So it will be 3,390 times 10 to the power 3 all what? Squared. Why times 10 to the power 3? We are converting from kilometers to what? To meters. So we have to multiply by what? By 1,000. Okay? So multiplying by 1,000. Okay? I forgot to put the mass of the probe there. So it's 6.67 times 10 to the power negative 11 multiplied by a mass of planet Mars, and then times mass of the probe, and then divided by the distance between their centers, which is 3,390 times 10 to the power 3, converting kilometers to what? To meters all squared. Then we will get the mass of the probe in what? In kilograms. So use your calculator to get the mass of the probe, and the mass of the probe is what? Is 900. So the answer that we're expecting here is what? It's 900. Okay. All right. Then another method that you can use, right? Another method that you can use, okay? You can maybe start by calculating acceleration due to gravity on planet Mars. Remember, this probe is on planet Mars, ne? So what is acceleration due to gravity on planet Mars? Is G equals to G m over what? Over R squared, ne? G 6.67 times 10 to the power what? Negative 11 multiplied by the mass of planet Mars, which is 6.39 times 10 to the power what? 23, and then the radius is 3,390 times 10 to the power 3 all what? All squared. Then we'll get acceleration due to gravity. Okay, so what are we getting for acceleration due to gravity? We have 6.67 times 10. I think I have it here. So times 10. So let's double check. The acceleration due to gravity, yes, is 3.71. Ne? So it's 3.71. So 3.71 meters per second squared. Okay. Then we have acceleration due to gravity, which is 3.71 meters per second squared on planet Mars. Then weight. What we are looking for? What the mass, ne? All right. So the mass, it's weight equals to what here? Weight equals to what? Mg. All right. So weight equals to mg. Remember, weight is the gravitational force. All right. Weight is the gravitational force that the Earth exerts on object on or near its what? Surface. So the weight it's given is 3,000. Let me double check that. 3,338. 3,338. And then we're looking for mass. Multiply that by 3.71. Then the mass will be what? 900 what? Kilograms. So this is another method that we can use to calculate what? The mass of the probe, right? Then calculate the weight of probe on Earth, right? The weight of probe on Earth. So how to calculate weight of probe on what? On Earth. Okay. Okay. The weight on Earth is given by what? By mg. Okay. Then the mass, we got the mass. It's what? Is 900. Remember what I said to you? Even if I can move from planet X to planet Y, if my mass is 900, right? Or if the mass of an object, for example, the mass of this probe is 900 kilograms, so it will remain 900. So what? But what is different is the acceleration due to gravity. So what is the acceleration due to gravity on planet Earth, according to our data sheet, is 9.8. Then we are going to have what? 900 times what? 9.8. And we are 900 times 9.8, it gives us what? 8,820 what? Newtons. So that is the weight of this probe on planet what? On planet Earth. Okay, another question. So this is the marking guideline, and we also got 8,820 newtons for 3.3, and then for 3.2 we got 900 kilograms. Okay, then another question. Planet Y has a radius of 6 times 10 to the power 5 meters, right? So we have a planet Y here with a mass, not the mass, but with a radius of 6.6 times 10 to the power 5 watt meters, right? A 10 kilogram mass weighs 20 newtons on the surface of planet Y, all right? So a 10 kilogram mass weighs 20 newtons on the surface of planet Y. They want us to calculate the mass of planet Y. Okay? They want us to calculate what? The mass of planet Y. So we are having two objects here. Okay? So the two objects, it's what? It's what? The planet and then this object. And so we are having this object on planet what? Y. So this object is on the surface of planet what? Planet Y. Okay? So they want us to calculate what? The mass of what? Of planet of planet Y. Ne? Okay? The mass of planet Y. We have what? Two objects here. F equals to what? G M1 M2 over what? Over R squared. Right? So this object weighs 20 newtons. So weight is the gravitational force. So I'm having 20 there. 6.67 times 10 to the power what? Negative 11. Then we have the mass of this object as 10. And then the mass of this planet, I'll use M there. So this is the mass of planet what? Planet Y. And what is the distance? Remember, this object is on the surface of that planet. Ne? And what is the radius of that planet? The radius of the planet is 6 times 10 to the power what? 5. 6 times 10 to the power 5 what? All squared. Then we'll get the mass of planet what? Y in what? In kilograms. The mass of planet Y in what? In kilograms. Okay? So what is the mass of planet Y in kilograms? So we have 6. Here we'll multiply by what? You have 6. Yes. So it's 6.67. Multiply that by 10 to the power negative what? 11. Right? And then divide that by what? Divide that by what? 6 times 10 to the power 5. Right? All squared. Okay. All right. So it's 6.67, 6.67 exponent negative 11, right? Oh, times 10. I forgot 10 there. What are we getting? Okay. All right. You divide that by what? 6, open bracket, 6 times 10 to the power what? To the power 5. All what? All squared. Okay. Then 20 divide that by answer, ne? Right. So we want the mass of the planet. I'm not sure. I don't know what is wrong with this calculator, but it's 6.67 times 6.67 multiplied by 10 to the power what? Negative 11. Okay, times 10. Exponent negative 11. Okay, then you multiply that by 10, divided by 6.6 times 10 to the power 5 all squared. Okay, all squared. Okay, then so here I'm getting what? 2 times 10 to the power what? 11 what? Kilograms. Okay, so what they wanted us to do here is to calculate the mass, right? So one, it was to choose the correct equation. After choosing the correct equation, you are given the weight, and then you have the gravitational acceleration, you have the mass of that object, and then you calculate what again the what the mass of what? Of planet what? Of planet Y. All right. Then I'm checking if we have another method that we can use here. All right, so we have, unfortunately, we don't have weight on this planet, né? So there's no way that we can use another what equation. So let's check the second equation. So we have the planet, what the mass of planet Y. Then 4.2, the planet mass has an approximate mass and the radius of 6.39 times 10 to the power 23 kilograms and 3.39 times 10 to the power 3 kilometers respectively. All right, so we have the mass of this planet, or planet mass, which is 6.39 times 10 to the power 23, and we also have what? The radius, which is 3.39 times 10 to the power what? 23. So they want us to calculate the approximate magnitude of the gravitational acceleration of the surface, on the surface of what? Of this planet, which is planet what? Planet mass. All right, so they want acceleration due to gravity. So it's A, not A, but G equals to G M over what? Over R squared. Okay, so we have 6.67 times 10 to the power negative 11. Then multiply that by what? Mass of this planet, which is 6.39 times 10 to the power what? 23. Divide by R. Let's check R. R here is 3.39. Ne? So it's 3.39 times 10 to the power what? To the power 3. you multiply that by what? By 1000. Then why are we multiplying by 1000? 1000 all squared. Why are we doing that? Remember the distance there is in what? Not the distance, but the radius is in kilometers. So if the radius is in kilometers, then we need to convert those kilometers to what? To meters. All right, so that is why I multiplied by what? By 1000 there. Then we'll get acceleration due to gravity in meters per what? Per second squared. But what was important here, the correct equation from the data sheet, number 2, we are given the mass is 6.39. Remember, this m is mass of the planet, so in this case is 6.39 times 10 to the power what? 23 there. So to the power what? 23. Then from there, it is the radius. The radius is given in what? In kilometers. Then we convert kilometers to what? To meters. Then we'll get acceleration due to gravity on this planet in meters per second what? Per second squared. All right. Then, yeah. So here they're only looking for what? Acceleration due to what? Due to gravity. Okay. Then another structured question. A research satellite has a mass of 3.4 times 10 to the power 3 kilograms. It orbits the Earth at a distance of 2.32 times 10 to the power 6 meters from the center of the Earth, which has a mass of 5.98 times 10 to the power 24 watt kilograms. So this, we have it in our data sheet, right? So fortunately it's also given, but always we are given the mass of what? Of the Earth. We are given the radius of what? Of the Earth. We are given acceleration due to gravity on planet Earth. We are also given what? Gravitational what? Constant, right? So you okay, research satellite has a mass, so the mass of the satellite is this, and the mass of the Earth is this, and then the distance it's 2.32 times 10 to the power 6 meters from the center of what? Of the Earth. Calculate the gravitational force that the Earth exerts on what? On the satellite. Calculate the gravitational force that the Earth exerts on what? On the satellite. Okay, so the gravitational force that the Earth exerts on the satellite is given by F equals to G m1 m2 over what? Over r squared. Okay, then this is 6.67 times 10 to the power negative what? 11. Mass of the planet Earth 5.98 times 10 to the power what? 24. We are also given what? The mass of the satellite. Ne? The mass of the satellite is 3.4 times 10 to the power 3. 3.4 times 10 to the power what? 3 over r. What is the distance between the centers? Is 2.32. 2.32 times 10 to the power 6 what? Meters, all what? All squared. Then we'll get gravitational gravitational force in what? In newtons. Okay, so what is the gravitational force in newtons? Let's calculate. So it's 6.67 times 10 exponent negative 11. Okay, multiply that by 5.98 times 10 to the power what? 24. Multiply that by 3.4 times 10. So it's 3.4 exponent what? 3. Okay, divide that by 2.32 exponent what? 6 all squared. Okay, so here I'm having what? 2.52 times 10 to the power 1, 2, 3, 4, 5 times 10 to the power 5 what? Newtons. Okay? Times 10 to the power 5 what? Newtons. So that is the gravitational not acceleration, but gravitational force between the satellite and the planet Earth, or the force that the satellite exerts on planet Earth, or the force that the Earth exerts on what? On the satellite. Remember, those two forces, they are equal in magnitude but acting in opposite what? Directions. So the magnitude of the force that the Earth exerts on the satellite is 2.52 times 10 to the power what? 5. Even the force that the satellite exerts on planet Earth, it is still 2.52 times 10 to the power what? 5 what? Newtons. All right. So application of Newton's third law. Right. Then the last question, right, which is 5.3. Right? Not 5.3. Let's look at 5.2. Name and state the law that is applicable to this situation. So name and state the law. So the name, this is very, very important. So in most cases, you'll get questions where they'll say, what? State Newton's law of universal gravitation in what? In weights. So now in this case, they want you to name and state it. Okay? So the name, it is the Newton's law of universal what? Gravitation. The name is Newton's law of universal what? Gravitation. Then state it. So to name it, it's a mark, right? Newton's law of universal what? Gravitation, it's a mark, right? Then to state it in weights, it's 2 marks for you to do that, all right? Each particle in the universe attracts every other particle with a gravitational force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. Then you'll get 3 marks. So you name and state what? The law that is applicable to this what? Situation. Right. Then this question, this is the last question. Another satellite of mass, half that of the research satellite, orbits at a distance half that of the research satellite from the center of what? Of the Earth. Ne? So we are having 2 satellites. Ne? So it's satellite A, all right, which is, we can say is the one that we're dealing with initially, all right. Okay, then we're having a new one now, right? Okay, so there are 2. So what are they looking for here? Calculate the net gravitational force on Earth exerted by the 2 satellites if the 3 objects are at positions shown in the diagram below. All right. Then for what satellite, the first satellite, what did we get for the first satellite? Ne? We got a 2.52, okay, times 10 to the power what? 5. That is the force that satellite A exerts on the Earth, or Earth on what? On the satellite A. Okay, so it's 2.52. Sorry about that. So it's 2.52 times 10 to the power what? To the power 5 newtons. Okay? Times 10 to the power 5 what? Newtons. And then we need now to find the gravitational force exerted by satellite B on Earth. Remember, we have the gravitational force exerted by satellite A on Earth. Okay? Now we are looking for what? The gravitational force exerted by satellite B on what? On Earth. So let's do that. Okay? So let's do that. All right. So one of the things that, okay, we can calculate it. F equals to G M1 M2 over what? Over R squared, which is 6.67 times 10 to the power what? Negative 11. So let's go back and check the mass of this satellite. Ne? We are told that the mass is half that of the initial what? Initial one, right? So the satellite B, its mass is half the mass of satellite A, right? and then it orbits at a distance half that of the research satellite from the center of what? Of the Earth. Remember, the distance between the center of the satellite A and the Earth is 2.32 times 10 to the power 6. Ne? But now, for satellite B is half of 2.32 times 10 to the power 6. Right? And then the mass of satellite A is 3.4 times 10 to the power 3. Okay? So if the mass of satellite A is 3.4 times 10 to the power 3, what about the mass of satellite B? We are told that is half the mass of satellite A. So we'll divide that 3.4 by what? By 2. Okay? So here I'm having what? Multiply that by what? What is the mass of the planet Earth is 5.98 times 10 to the power what? 24. The mass of satellite B is half the mass of satellite A. What is the mass of satellite A? Is 3.4 times 10 to the power 3. So here it will be 3.4 times 10 to the power what? 3 divided by 2, because we are told it's what? It's half. Over the distance is 2.32 times 10 to the power 6. 2.32 times 10 to the power what? 6. But we need to divide that by 2 because it's half the distance between what? Satellite A and what? And the Earth, right? So all squared. Then we'll get the answer here in what? In newtons, right? So let's find that answer. We have maybe before getting an answer, another method that we can use proportionality. Ne? Let's use proportionality, right? So you have F equals to G M1 M2 over what? Over R squared. That is for satellite. That is for satellite what? A. Ne? And then for B, it's F equals to, the mass is halved. Okay? So it's half G M1 M2. And then what about the distance? The distance is also halved. So it's 1 over 2R all squared. So what am I having here? I'm having 1 over 2 G M1 M2 over 1 over 4 what? R squared. Okay? Right? So I'm having 1 over 2, multiply that by 4 over 1, and then this is F, ne? Which is the force exerted by satellite A on Earth. Okay? So is 2, what here is 1 times 2, sorry, 1 times 4, which is 4, and then 2 times 1, which is 2. So it's 4 over 2, which is what? 2. Is twice F, ne? So nu, the force exerted by satellite A, what? B, on what? On Earth, is twice the force exerted by what? Satellite A on what? On Earth. So we can do this. 2, what is the force or the magnitude of the force exerted by satellite A on Earth? We got 2.52. So it's 2.52 times 10 to the power what? 5. So 2.52 times 10 to the power 5 times 2. What are we getting here? We are getting what? 5.04 times 10 to the power 5 what? Newtons. Okay. All right. So it's 5.04. So which means that even here it is 5.04 times 10 to the 5 what? To the power 5 what? Newtons. Okay. Then, so here is 2.52 times 10 to the power 5 newtons. And then between the Earth and satellite B, we got what? 5.04, ne? 5.04 times 10 to the power what? 5 newtons. So let's calculate what now? The net gravitational what? Force exerted on Earth by the two satellites, ne? So the force exerted by this is the force exerted by A on Earth. All right, this is going to be what? The force exerted by what? By B on Earth. Okay, so each particle in the universe attracts every other what? Particle, ne? So we can draw a free body diagram here indicating only the gravitational forces exerted by these two satellites on planet Earth. So this is going to be what? Planet Earth, right? Okay, so force exerted by satellite A on what? On Earth, ne? So the Earth will be attracted, okay, to satellite A. So this is the force A on what? On E. Okay, then the Earth is also attracted to what? To satellite B. So this is the force exerted by what? By B on what? On Earth. You can see that these two forces, they're acting in opposite what? Directions. Okay, they're acting in opposite what? Directions. So now let's calculate the net. Okay, so these are forces in one dimension. So for forces in one dimension, how do we calculate? For forces in one dimension, ne? Okay, we have net F net, or net gravitational force, which is going to be the force exerted by A on Earth plus the force exerted by B on what? On Earth. Okay, so the force exerted by A on Earth, right? You can see they're acting in opposite directions, right? So we can take left as what? As negative. So it will be negative 2.52 times 10 to the power what? To the power 5 plus 5.04 times 10 to the power what? 5. Then we'll get the magnitude of the net force on what? On planet Earth. So it will be so it's what here? Minus 2.52 exponent what? 5. So which is going to be what? 2.52 times 10 to the power what? To the power 5. So this is our answer. So here, when it comes to this question, one, you are supposed to calculate, which is what we calculated in 5.1, to calculate the force exerted by satellite A on Earth. We got that. And then we are supposed also to calculate what? The force exerted by what? By satellite B on what? On planet Earth. And then add the two to get the net gravitational what? Force. Right, so learners, today our focus was just on Newton's law of universal what? Gravitation, the multiple choice questions on Newton's law of universal gravitation, and also what? The structured what? The structured questions. So I think for today we are done. Thank you so much for joining this lesson.